Hello everyone. Last time we learned how to simplify exponents, but what if we have to graph um, functions that have a power, right? So hold up, I think the term was like power functions. There we go. What if we have to graph power functions? Now, what is a power function? A power function is just simply a function that has x, y equals x, and then some number as the power of x, which is not one, right? So this number is just a variable to represent. So it could be 1, it could be, or rather, it could be 2, it could be 3, it could be 4, it could be 5. This n could be any of these, right? And x is just the variable, so we don't, remember, this is a function, so x is the independent variable, and y is the dependent variable, right? So let's start by having an example right here. So how do we graph y is equal to x squared? All right. Now, of course, we could just do, x, y. So we could, or yeah, like that. Okay, what if x is 3, 3 to the power of 2? So if x is 3, we put 9. But this can take some time, and there is a better way and faster way to graph something like this. So I need to let you know the basic form. Right, so the how it looks without any modifications or anything, because we're going to be analyzing this equation later to see where we can graph it. All right. So this is how it looks. Okay, this is the stock one. This is the father equation, I think it's called, and you just go like this and like this, or like this. All right. If you know something about absolute value functions or equations, you would know that it's very similar, right? This is an absolute value one right here, and this is an exponent one. The absolute value one is more pointy, this one's more round, right? So, like the absolute value one, we can analyze the equation and find where to just graph this, right? And instead of the vertex, we actually call it the parabola. So here the parabola is 0, 0, right? So here is 0, 0. It's our parabola, and the parabola is just where, like, the middle and the lines stretch out from the parabola, right? So we have one going this way and one going this way. All right. So what if we have y equals x to the power of 2 plus 2? How do we graph this? Well, what we could do is just count 2 up. So this is 1, this is 2, and then plot a point, and this will be our parabola. So we can now just do the I guess you could say the rounded y, and we'd have something like this, right? So let's also do let's also do y is equal to x to the power of 2 minus 2, right? So here, when we added 2, it went up, the parabola, right? When we subtract 2, we go down, right? So this is our parabola here. So we just count 1, 2, right? We go 2 down, and then we plot a point, and then just do our simple, I guess, rounded V shape right here, right? Like this. So when it's subtracted by a number, we just go down that amount. When it's added by a number, we go up that amount. All right. So let me just go down. It's for the second example. All right. So let's say we have y is equal to, and let me just think of a okay. So y is equal to x minus 2 to the power of 2. Right? Now we have these in parentheses, and then it's to a power, right? So how can we graph this? Well, remember, we can still use the parabola thing. So let me just do this, right? But instead of going up and down, we go left and right. So what we do here is actually go 2 to the, 2 to the right. Now, this might sound confusing. Like in the last one, when we subtracted, we went down. But why do we go right when we subtract? Well, this is one of the rules. When you have these in parentheses, actually subtraction goes to the right here, right? So let me just like this, right? So I'm very bad at graphing. Like this and like this. Imagine this was an accurate graph, you would get something like that, right? So when it's in parentheses and it's subtracted by a number, you go right the amount of times that is subtracted by. How about we have y is equal to x minus or plus 2 to the power of 2, right? Here we would go 2 to the left, so 2 back, and then we would graph the parabola, which is right here, and we would, do our rounded V shape, right? So that's good. That's all good. But what if we have a mixed one? So let me just go down here and let me bring out a coordinate plane. There we go. Right. So how about we have y is equal to x minus 2 squared plus 2, right? So let's analyze this equation. We know when it's in parentheses and we subtract, we have to go right the amount of times that it's subtracted by, right? So we go right 1, 2, but we're still not done yet. We have this 2 on the outside. So we know when we add 2 on the outside, we actually go 2 up. So here we go 1, 2, and we end up graphing the parabola right here, which is the coordinate 2, 2, right? So let me just get this pen right here, and then we can graph it like this, or up like this. So it'd be like this, right? Good. How about we have another example, which is y is equal to x plus 2, and then let's see, sure, minus 2. So here we would go 2 down, so 2 down, and then 2 left, 1, 2. And then we would end up graphing at negative 2, negative 2. So let me just bring this green pen, I guess. And this would be our parabola right here. And then we just branch off like this. There we go. All right. So let's say we have a cubed function. So we have y is equal to x to the power, or y equals to x cubed, or to the power 3, right? How do we graph this? Well, it's different than the squared one, but we can still figure it out. So, since we're not adding or subtracting or anything, we'll just do the stock one. So we just go here, and then one goes right and up, and then our line goes left and down, right? So you kind of have them going the opposite direction, and like this one's flipped, right? So how would you be able to so this point right here where they both branch off is called the, I think, inflection point. So the inflection point is pretty similar to the parabola and is where these two lines branch off, right? So if we were to, let's say, y is equal to x cubed plus 2, we would just end up going 2 up. So this is 1, this is 2, and then we just graph this using another color. And then we'll just do like this and like this. Simply like the one below it, right? So yeah, the rules that apply to the squared one also apply to this one. All right, so how about we try to read from a graph, right? So how about we try to find the equation from a graph? So let me just turn this into black right here. There we go. And let me just see. Okay, so 1, 2, 3, 4, 5, 6. Let me just label this graph right here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. So let's try to read from this thing. I will do a random spot, I guess. All right. So let's try to read from this. All right. So here we go. 2. So 2. We go 2 right, and then here 1, 2, 3, 3 up. Right. So now we can read this graph. So y equals to what? Y equals, so when we know when we're going right, it's going to be x in parentheses, and then minus, and then we're going right 2 times, so we end up writing 2, and then we close off this parentheses. And remember, this is a V shape. It's not like the other shape, which is somewhat like this, right? It's a V shape, or I guess a circle, like a rounded V shape. So we know it's to the power of 2. And then here we end up going 3 up. So we can just add 3, right? So let me just do another one right here. Or like this. So our inflection point is 3 back or 3 to the left and 1 up. So let's try to write this equation here. Y is equal to what? So first of all, we know when we're going 3 back, we have x in parentheses and then x plus something. But here it's 3 because we're going 3. 3 back or 3 to the left. So plus 3. Right, so we got this covered, but how do we make it go 1 up? Remember, we add by 1. Of course, as you can see, this is the one where it goes like this and like this, so this ends up being cubed. And then here we can just add 1. So this is the equation for this one. So now that you know how to graph these equations and analyze them, and how to analyze the graph and find these equations, I hope that you are ready to move on, and I wish you the best of luck. See you later.